Revision of variance and standard deviation from last lecture. This is what we have done previously. We learned how to use this formula. We calculated variance for car dealer 1 and car dealer 2, and then we compared them together. We calculated standard deviation. We calculated sample variance. Okay, now let us apply what we have learned so far on a business application. So you are thinking of setting up a knowledge intensive business in China, let's say microprocessor chip making. So where you are going to locate? Does it matter where you locate it? Yes, it matters. Knowledge intensive businesses rely on human capital. For example, chip making business require engineers. You need high-tech professionals who would help you run the business. So yes, knowledge intensive businesses rely on human capital. So where we locate, it matters. Do we have the required human capital availability in that region? Yes. Graduates are a good source of human capital. Okay. It's no accident that Silicon Valley is located next to several leading universities in California. Yes, true. Strategic advantage of Silicon Valley's closeness to top universities like Stanford University, University of California, and many others. So what is the benefit? You have access to talent. Graduates who are well versed in the latest technology and business strategies. You will have access to innovation and research. Universities are centers of research and innovation. Moreover, close proximity to such university means networking and collaboration. Being close to universities makes it easier to network with academics and researchers. And then finally, recruitment opportunities means companies situated near these universities have a better opportunity to recruit top talent directly from the campus. So yes, it matters where you locate. So how can we measure human capital? Possible measures: proportion of a population with a degree. How many are degree holders among the population? And proportion of the workforce with degrees. Those who are working, out of those, how many have got the degrees? Let us look at the first indicator for a sample of 15 Chinese provinces. There are 31 provinces in China. And let us discuss this example here. It says if there is little or no variation in human capital across provinces, geographical location won't matter for this variable. So it means if human capital is the same across all these provinces, so it doesn't matter whether we locate in province A or province B or province C. So here we have human capital in Chinese provinces. Percentage of population with an undergraduate degree in a sample of 15 Chinese provinces. We have got these 15 provinces right here. And then percentage of population with an undergraduate degree, 54% in Beijing, 11% in Inner Mongolia, and so on. We got the mean, deviation from mean, square deviation, and finally a summary of median, mean, standard deviation, variance, range, and mode of this data right here. So here we got, so this is the median of the percentage of population with an undergraduate degree. This is the mean, variance, standard deviation, and range. This is the most important part. Range, that is the spread. So the large range clearly it tells us that there is a lot of volatility, lot of variation in the data. So the range is large. So that means location is likely to matter. So the following slides calculates the variance and the standard deviation. This is your deviation from the mean, that is x minus x bar. And this is the deviation squared, right? So you add these all up and divide it with, so what you got? Summation x minus x bar squared upon n minus 1. So that is the variance of the sample. Remember, there are 15 provinces, and 15 minus 1, that is 14, right? So that's the sample variance. So sample variance is 159.11. If you take the square root, it becomes the standard deviation. So what do we interpret from this? Key points, okay? Okay, it says recall that the variance measures distances from the mean, that's deviations. It sums the square differences and divides by n for the population variance or by n minus 1 for the sample variance if we only have a sample of data, that is n minus 1, to find the average square deviations from the mean. This is it. Variance measure distance from the mean. It sums up the square differences and then divides it with n for the population variance and n minus 1 for the sample variance. And then it says the standard deviation is the square root of the variance, and it's a measure of distance from the mean that translates the variance back into the original units of data. Let me show you. This is the variance, that is the square deviation sum divided by n minus 1, and then standard deviation is the square root of the variance, and this is again the original units of the data. In this example, we don't have units, we have percentage. So standard deviation, ladies and gentlemen, is 12.61%. In our previous lecture, we learned how to measure covariance, how to derive covariance, and then determine the Pearson coefficient correlation, which is range bound. It cannot be greater than 1 and it cannot be less than minus 1. So it's greater than equal to minus 1, less than equal to plus 1. And we discussed in detail what this negative and plus mean and what R0 means. Please watch the previous lecture and you would get the full understanding of what we are talking about. Let us consider the two cases of the following variables. Here we have books read X and exam marks Y attained by students in 2023, for example. So do you think there is some sort of relationship between them, positive, negative, or 0? We discussed and we even determined the relationship between X and Y. We calculated Pearson coefficient correlation, we calculated covariance, and we determined coefficient of correlation to be 0.83. So yes, there is a strong positive correlation between books read and the exam marks. And does X cause change in Y? Yes, it is the independent variable. Books read is the independent variable and it causes the exam marks to be either higher or lower. So yes, there is a positive correlation, and X is the independent variable and Y is the one that depends on X. Then number of people carrying an umbrella X and amount of rainfall on a particular day, time series data. Yes, indeed, there could be a positive correlation between the number of people carrying an umbrella and the amount of rainfall on a particular day. This relationship would likely to be because more people choose to carry umbrellas when they expect rain or when it's raining, making it logical to observe a higher number of umbrellas on days with more rainfall. But does X causes rainfall? Of course not. Does X, books read, causes exam marks to be high? Yes. So there is causation, there is correlation in this case. Here there is a correlation, but there is no causation. Number of umbrellas are unrelated to rainfall. Number of umbrellas do not cause rainfall, but number of books read affect your exam marks, gentlemen, ladies. So this is the graph representing books read and exam marks percentage. So you can see there is a positive trend, so they are positively correlated as far as the data is concerned. Umbrellas and rainfall, daily data, time series data. So you see here, there is clearly an upward sloping line. So there is a positive correlation between the number of people on any day spotted with an umbrella and amount of rainfall on each day. We discussed this concept covariance in our previous lecture. So we can measure the extent to which two variables X and Y, like number of books read and your exam percentage, or number of people with umbrella and the rainfall. So we can measure the extent to which these two variables vary, and this covariance of X and Y we learned how to calculate in our previous lectures, and this is how we do it. Summation X minus X bar into Y minus Y bar upon N, that is for covariance of the population, or divided by N minus 1 for the sample covariance. We discussed this in detail. Please see my previous lecture on this topic and you will see we have done everything. Same table, student number 1 read 3 books, got 56%. Student number 3 read no book, got 45. So same table, we use this table to calculate the covariance we discussed in detail in the previous class. Now what we have here, So we've got exam marks percentage in blue and books read in green. There appears to be a trend where students who read more books tend to score higher on the exam. This is most evident with student number 5. He read 4 books and he got the high score. So yes, apparently, but this is not true here for the case of student 3. He read no book, yet he got nearly 45%. So it's not a perfect positive correlation, but it is a positive correlation, and we tested this using a t-score in the last lecture. All the slides that are coming, we have already done them. This is just repetition, just revision. The covariance gives us a measure of how much x and y vary together. Yes, we know. And this is how we calculated the covariance of x and y. Absolutely. Same slide, previous lecture. Pearson correlation coefficient lies between -1 and +1. We know. Yes, it's range bound. This is the interpretation we have already made. If it is negative, there is an inverse relationship between x and y correlation. And if it's positive, there is a positive correlation between x and y. And if it's 0, there is no correlation. And the absolute value, ignoring the negative sign, shows you the strength of correlation. We have discussed every bit of it in the previous class. This is the formula we use to calculate the coefficient of correlation, discussed in detail. Same slide from the previous lecture, and that's what we calculated in our previous class. So this number we calculated, is this statistically significant? We discussed every point in this slide in the previous class, and we calculated the t-value to be 2.6, and then we conducted the one-tailed test, t-distribution. I hope you remember. So yes, coefficient of correlation, rho, is positive, equal to 0.83. This means that there is a positive correlation between the number of books individual students read and their exam marks. However, we could attain this result by chance. For this, we are going to test our to see how significant this is. So we need to check that rho is significantly different from 0. To do this, we use a test t-test. We used a test t-test in our previous class. So here's a little background knowledge or history related to t-test. This test uses the t-distribution introduced by W.S. Gossett, a statistician who wrote under the pen name student. This exact slide was also discussed in the previous class. The t-distribution is like a normal distribution but flatter, yes. As the number of data observations, like in our example, is 5. As the number of data observations in our example increase, the t-distribution converges to a standard normal distribution. This was discussed in detail as well as with the graph or the look. And Pearson correlation coefficient follows a t-distribution, and we can use a test to see if r is significantly different from 0. This was done exactly in the previous class. We inputted the values in the previous class and we determined our t-score to be 2.6. Okay. Using the table one-tailed test, the theoretical value of t using a 95% confidence interval. Let us discuss what is a confidence interval. Confidence interval is a range of values used to estimate the true value of a population parameter. For example, let's take a simple example. Let's say there is a large jar full of candies. And imagine you are trying to guess how many candies are in this large jar at a party, for example. So what you do, you take a few samples. You take some of your friends do. So each guess by taking out and counting the candies. So based on these smaller counts, you estimate the average number of candies per handful. You took some, your friends took some, A took some, B took some. So each one of you got some handfuls of candies, right? So you make an estimate based on these smaller counts. You try to estimate the average number of candies per handful. Then you create a range. To account for differences between handfuls, you create a range around your average estimate. Let's say you think that average is around 6 candies per handful, right? So what you do, you create a range around your estimate where you are probably sure the true average lies. 7, maybe 5. So this range around your mean, this range, this gap is your confidence interval. If you say it with 95% confidence, it means that you believe that there is a 95% chance that the true average number of candies per handful falls within this range. So basically, confidence interval helps you say, based on my sample, I am this much confident that the true value is between here and there. That is confidence interval in the simplest possible way. Next concept, we have degrees of freedom. Imagine, same example, the example involving candies in a jar. So imagine you have 5 friends who need to share 100 candies amongst themselves. So they decide to divide the candies equally, so which means each gets 20. So your friend A gets 20, B gets 20 first, then C gets 20, D gets 20, and the last one, unfortunate one, E. So the number of candies the 5th friend E gets is no longer free to be chosen. He is no longer free to be chosen. He will get what is left. So basically, when you have 5 friends, the degree of freedom is not 5, it's 4. Because the last friend, unfortunate one, he gets what he gets at the end. So the degree of freedom essentially is the number of friends in this example who can freely choose their candies before the last friend gets his share at the end of the whole process. But in statistics, this concept helps in understanding how many values can vary in a data set or in a formula calculation before the rest are determined by the existing constraints. So when you say n minus 2 degree of freedom, what does it mean? This specific form n minus 2 is often used in statistical tests like regression analysis, where 1 degree of freedom is lost due to the estimation of one particular parameter like mean or intercept. Another degree is used up when estimating another parameter like slope in a simple linear regression. Let's take it back to the previous example, the candy one, you'll get better idea. So in a candy sharing example, we have 5 friends, and in this new adjusted scenario, using n minus 2 degree of freedom means you would only have 3 friends who can freely choose their amount of candies without constraint. And the candies for the last 2 friends would be determined based on how many are left after the first 3 have taken their shares. So in statistical terms, n minus 2 degree of freedom adjusts the calculation to account for these parameter estimations, ensuring that the statistical method remain valid and accurate. In practical applications such as what we will be doing soon, hypothesis testing or building confidence interval, this ensures that the test appropriately accounts for the sample size and the parameter estimates. This is our t value, and this is the theoretical value of t using 95% confidence interval with n minus 2 degree of freedom, and this is determined using the table. Let me show you. df, degree of freedom, n minus 2, 5 minus 2, that means 3. And since we are using 95% confidence interval, that means then we need to determine whether it's a one-tail test or two-tail test to determine the theoretical value of t. One tail versus two tail. The correlation coefficient that we want to determine would be on one tail test. Why? Because we want to establish that it is significant and positive. Because numbers of book read and the score, we are looking for a positive correlation between them. Significant positive. We are not interested in this. So for this reason, we are going to go for one tail test. Two tail test the hypothesis we'll discuss that R is significantly different from 0, but it could be either positive or negative. But our concern here is that we are interested in this part only, positive and significant. So degree of freedom 3 and critical value at 95% level of confidence or 5%, it's 2.35. This is your theoretical value. So this chart here, it illustrates the t distribution with the degree of freedom n minus 2. In our example, it's 5 minus 2, 3, where n is the number of observations. We have 5 observations. So here is a breakdown of what this means in the context of the data we are discussing. Here, this orange line here is the t distribution curve. This represents the t distribution for 3 degrees of freedom, the example we are carrying on. The curve shows the probability density of different t values from 0 to 4 and 0 to minus 4. This green dashed line here you see, this line represents the observed t-value from our data, which we calculated as 2.6, and it falls within the critical region. Remember these red marks here, these red regions or pink regions, these are the critical region left and right. So your value, your t-value, it falls within the critical region, suggesting that the results are significant. These blue dashed lines that you see, these are your critical values, 2.35 plus, 2.35 negative. Let me show you this one. These are the critical values. So these blue lines you see here, they mark the 95% confidence interval in a one-tail test. Right here we're talking about region. So any t-value exceeding this critical value in absolute term falls into the critical region here, indicating it is statistically significant. These red regions here, they represent critical regions. If the observed t-value falls within these areas, it suggests that the difference the difference observed between number of books read and the exam score, the example we're carrying, is statistically significant and not likely due to random chance. So finally, since our observed value 2.6, it exceeds the critical value of 2.35 in a one-tail test at 95% confidence, it indicates that the results are statistically significant, and this also suggests that there is a meaningful relationship between the number of books read and the exam score. So means reading more books is associated with the higher exam scores based on our data set we discussed. So this result supports the hypothesis that variable X, books read, and variable Y, exam score, they are positively correlated, and this correlation is statistically significant at 95% confidence level. So a two-tailed test will test the hypothesis that R is significantly different from 0, but it could either be positive and significant or negative and significant. So let us now try to do it using the two-tailed test. But before that, how do we know whether to use one-tail or two-tailed test? Generally, this must come from our theoretical hypothesis, like what our hypothesis was, that in this example, our hypothesis is that the more relevant books a student reads, the higher their exam marks. So hence we expect a positive correlation between books read and the exam mark. So therefore we use a one-tailed test. What if we use two-tailed test? What will happen? I'll show you. So this time now these are our critical regions. Our observed value is right here, 2.6, right? And critical value at 3 degree of freedom is 3.18. So it's plus 3.18 and it's negative 3.18. And your observed value happens to fall outside the critical region. So our observed t-value does not reach the critical region of plus 3.18 or negative 3.18. So it does not fall into the critical region. So this indicates that there is not enough evidence to conclude a statistically significant difference in the mean exam score based on the number of books read. It means there is no significant relationship or significant association between the number of books read and the score in exam, either positive or negative, at the confidence level corresponding to the critical t-values we discussed at 95% confidence interval. So two-tailed test isn't suitable here. Where it will be suitable, let us discuss the example. A two-tailed example. Suppose we were looking at the relationship between market power and efficiency. Interesting. There are two competing theories. Greater market power means less competitive pressure to reduce cost and therefore less efficiency. Means if you are a very strong business in a certain industry, you hold market power. Since you hold market power, you face little competitive pressure. Since you face little competitive pressure, you are not concerned about reducing your cost. Since you are not concerned about reducing your cost, so you are less efficient. So this is one of the theories, that since you are strong, you are powerful, you are also inefficient, right? So greater market power, less efficient. And the competing second theory Lower cost means greater efficiency and higher market power. Means a business that had lower cost, it is efficient. Since it is efficient, it will have a higher market power or market share. So interesting, we have got these two competing theories totally in the opposite direction. So in this case, we should use our two-tailed test, because a priori the relationship between market power and efficiency could be positive or negative. Means our knowledge based upon theoretical deduction means either there is a positive correlation or there is a negative correlation, right? So it means it could be positive or negative based upon our knowledge or conclusion from theoretical deduction. We haven't yet conducted any observation or any experience yet. So in this case, we cannot rule out the possibility that two variables are positively related or they may be negatively related. So what we would do in this case, we'll construct a null hypothesis suggesting that there is no correlation between market power and efficiency. It suggests that any observed relationship in the data is due to sampling error or is purely coincidental. The alternate hypothesis states that there is a correlation between market power and efficiency, which could be either positive or negative. So it reflects a kind of uncertainty about the direction of relationship. It could be positive, it could be negative. So the test is two-tailed test because we consider the possibility that the relationship between market power and efficiency, it could be positive and negative. Positive means greater efficiency means you have higher market power, and negative means greater market power and less efficiency. So they can move in the both ways. So that's why we will conduct a two-tailed test. Another example, suppose we are interested in the idea that unemployment U and economic growth G are related. So we might formulate the hypothesis that the rate of growth of an economy, G, is associated with the changes in the rate of unemployment. So what we understand is that when there is higher economic growth, the unemployment rate would be low. That is what common sense tells us. And that these two variables are inversely related. As you can see, as growth falls, the change in unemployment rate rises. So when growth falls, less economic opportunity, unemployment rate goes up. So there is an inverse relationship between these two variables. Here are some time series data on growth rates and changes in the unemployment for Japan. Let's see. So this shows you the annual percentage rate of growth in real gross domestic product, GDP. You can see when the growth rate is negative, the unemployment rate went up, and when the growth rate was high, let's say here, the unemployment rate fell down. So there clearly is an inverse relationship as suggested by just look at the data itself. So we can make a scatter plot of this two set of data series. Let me show you. And as you can see, the data points, they appear to be negatively correlated. It looks like there is a negative relationship between G and U apparently. So drawing a line through the data makes it clearer. So there is a negative relationship between changes in the unemployment rate and the changes in the GDP growth rate. So here is our interpretation quickly. An inverse relationship, we can see that there is the rate of growth increases, the unemployment rate falls, or vice versa. As the rate goes up, the unemployment rate falls, and when the rate growth falls, the unemployment rate goes up. So the rate of growth falls, unemployment rises. So the rate of unemployment and the rate of growth are negatively related, same thing repeating. So there is an inverse relationship and slope of the line is negative, we just saw. This is the negative sloping line. A positively sloped line would be like this. So our hypothesis should come from theory. And what theory? Keynesian theory. It predicts that GDP growth rate and unemployment, they are negatively related. Means when the GDP grows, the rate of GDP increases, the rate of unemployment should fall. So according to this theory, G and U are inversely related. So we can test this hypothesis using Pearson correlation coefficient by setting up the hypothesis called the alternate hypothesis and a null hypothesis. Let me show you. So to test our hypothesis, we suggest the null or empty hypothesis that R is 0. There is no relationship. And the alternate hypothesis that R is not 0. R is less than 0, that is, it's negative. It means there is an inverse relationship. So formally we write, our null hypothesis suggests that there is no correlation. An alternate hypothesis is that R is not equal to 0 and it is less than 0 means there is a negative relation. So this is setting up of one-tail test. We have ruled out the possibility that G and U are positively correlated. So we are looking for the negative side of it. Just like the way we discussed a little while ago, in two-tail test, we use our t-test using both the positive and the negative tails of the distribution. We just discussed it a little while ago. And we will refine upon this concept as we proceed into this next lecture. So from theory to hypothesis, whether we set up our hypothesis test as two-tail or one-tail test, we must decide considering the theoretical possibilities first. So in the case we are discussing the relationship between growth and unemployment, there are good theoretical reasons to hypothesis that they are inversely related. That high growth rate means unemployment rate will fall. Clearly, that's understandable. There is a negative correlation. And it further says a little understanding of the business environment, economics, suggests that it does not make much logical or theoretical sense that as GDP growth rate rises, unemployment growth rate doesn't make sense. When GDP growth rate is high, it means there are more job opportunities, so unemployment rate should fall, right? So therefore, we may want to rule out a positive relationship in this arrangement. So if we are not sure whether a relationship is positive or negative, only then you should go for a two-tail test.